Hi, this is Algebra 1, Module 6, Lesson 6. How does it grow? So now we're going to practice those different things we have learned about quadratics, comparing them to linear and exponential, or maybe it doesn't apply to any of them. So for each of the relations given, and there's a number of them, we're going to identify whether or not it's a function. We'll determine if the function is linear, exponential, quadratic, or neither. Describe the type of growth, and then create one more representation. So our first one, the plumber charges a base fee of $55 for a service call. Go ahead and mark some information here. $55 for a service call plus 35 per hour for each hour. This relationship between the total price of the service call and the number of hours worked. Well, this one um, is, let's type so we can read it easier. So for this one, A, I would say this is a function because the growth on that is linear, right? You have a set fee and then you're repeating $35 per hour. So that would be the slope. B, it's describe its type of growth, which means it has a slope. So it has a constant rate of change. And then my next representation, I'm going to write the equation for it because I want the cost equals $55 plus $35 per hour of work. So I'm going to do the equation for that one. All right, for number 2, let's do this one up here. So 2a, this is a function. So b, this looks like a quadratic function to me because of its parabola here. C, so its type of rate of change, if it's quadratic, then it's linear. And then D, what I could do for this one is, I don't know about its equation at this point, but I can plot some points on there. So if I start with -1 or even -2 on there, so I'm going to do an x here, x and y table. So my x, if I do -2 for my x, my y is 1. If I do -1 for my x, my y is 4. If I do 0 for my x, my y is 5. And then I'm going to do 1, gets me back to 4. I'm going to scoot that up a little bit so I can go all the way to 2. 2 then would be 1. All right, so I got those points on there. Second one, done. Third one. Okay, well, it looks to me like it's a function. There's no two lines covering each other. So A is a function. Looks to me like it is going down to a point that's going to get smaller and smaller, which makes it exponential. No parabola curve on there. And so exponential has an exponential rate of change. And then for this one, let's see if I can figure out some of these points. It's going from 8 to 4 to 2 to 1 to half. So I'm going to say f of x equals, I think it's 0.5 to the x power, because I go point half to the -1, that flips it to be a 2, and so on. All right, 4. This is definitely a function, and I can see that I have a squared in there, so this one would be quadratic. C, if it's quadratic, then it has a linear rate of change. Another representation. I have a few options here. I could graph this. I could make a table. I think I'll go ahead and I go ahead and do a table for this one. Graphing's a little tricky for me right now. We're going to do X and Y. So if X is, let's just do 0. So if X is 0, then 0 minus 2 is negative 2. Negative 2 squared is 4. 4 thirds plus 4 would be 1 and 1/3, so that'd be 5 and 1/3. That was kind of an ugly number. Let's try 1. So 1 minus 2 is a negative 1. Negative 1 squared is 1. 1/3 plus 4 is 4 and a third. That'd have been tough to graph. 2. 2 minus 2 is 0. 0 squared is 0. 0 times 1/3 is 0. So this one is 4. And let's do 3. See what happens with this one. 3 minus 2 is 1. 1 squared is 1 times 1/3 is 1/3. So this is back to the 4 and 1/3, which tells me that if I do 4, I will probably end up 5 and 1/3. All right, there's my number 4. 5. 5, well, A, that is not a function because I've got all sorts of points that are 12 has 2 answers, 10 has 2 answers, 7 has 2 answers, all those, which means the rest, B through D, can't answer. You can't do anything if it's not a function. All right, 6. This one, hey, that looks very similar to our one we had before. A, this one is a function. B, I have no exponents. It doesn't look like I'm going to have any exponents at all, so this must be linear. Linear has a constant rate of change. And I'm going to go ahead and do a table again because, as I said, it's hard for me to do graphs on these. So you could graph this one if you really wanted to. So we're going to go 0. Oh, wait, we did 2 last time, didn't we? What we started with? 0, negative 2? Let's start with negative 2. So negative 2, give myself just a little more space here. Negative 2 minus 2 is a negative 4. That's going to get ugly. Let's go with positive 2. Positive 2. 2 minus 2 is 0. 0 times 1/3. So that one's a 4. That one's lovely. That was a good one. Let's do something that's going to multiply by 3 nicely. Let's do 8. 8 minus 2 is 4. Nope. 7's 5, 6. 6 minus 2 is 4. 5 minus 2. There we go. 5 minus 2 is 3. 3, a third of 3 is 1. 1 plus 4 is 5. Which means I'm going to have to go up to 8 minus 2 is 6. A third of 6 is 2. 2 plus 4 is 6. So if I go up 3 over here, I can go up 1 on this side. There's my slope of 1/3, right? So 0 means I should be starting, we got the minus 2. So my first coordinate is 2, positive 4. Oh, bringing back memories from module 2. All right, 7. 7, 10, 20, 30. Looks like I'm going up. Let's go ahead and just write some stuff in here. 50 minus 12.5. You should be able to see what's going on here. If we do our t minus 12.5 is 37.5. I don't know why that's not writing. A 112.5 minus 50 is 62.5. 200 minus 112.5 is 87.5. It's not typing, writing at all for me. Okay, so our first difference is not the same, but let's see what our next one is. So 62.5 minus 37.5, that's 25. Why that's not writing? Okay, 87.5 minus 62.5, oh, is also 25. So that means this one is a, it is a function, and we can see that, put over here, a is a function. You can tell that it's quadratic because it has the second difference, which means it has a linear rate of change. And D, well, we haven't talked about equations. We already have the table. I'm going to have to draw a graph on this one. So let's see what I can do here. I'm going to do a small one right here. And let's see. I need to be able to go up to 1. So speed we'll do 2, 3, 4, 5, 6, 7. So we'll do 10, 20, 30, 40, 50, 60, 70. And then I need to get up to 600. 1, 2, 3, 4, 5, 6. We'll go by hundreds. So 10 is pretty low down here. Let's get a different color. Pretty low down here. 20 is 50, so about halfway up. 30 is 112, which means, oh, this is going to be tiny. 40 is 200, so that's even with that guy. 50 is 312, so now I'm above this one. 60 is 450, 1, 2, 3, 4, 50. 70 is 612, I'm clear up here. And because there's no information in between, we're just going to leave it dots and discrete. So not a great graph. Apologize for that, but best I can do at the moment. You guys will use graph paper and do much better, I'm sure. All right, relationship between the number of dots and the figure. So figure 1 has 1, 2 has 3, 3 has 6, 4 has 4, 7, 8, 9, 10. So what are we doing here for this one? Well, it's a +2, +3, +4, which means I go +2, +3, +4. That means the second difference is a +1. So that should tell us A, 1, this is a function. B, it is a quadratic function, which means it has a linear rate of change. And I think for D, let's make a table on this one. So we have our T and our dots. So number 1 has 1 dot, 2 has 3 dots, 3 has 6 dots, and 4 has 10 dots. Just a little bit so we can see it. All right. Like that lines up a little better. All right, that's 8. 9. The rate at which caffeine is eliminated from the bloodstream of an adult is about 15% per hour. The relationship between the amount of caffeine in the bloodstream and the number of hours and the time the adult takes the drink is about 500 milligrams. So we've seen these kind of problems before. Which means A, it is a function. B, 15%. That means we're multiplying, so that one is exponential. C has an exponential rate of change. And so D, if I'm going to do my equation, my caffeine equals, well, I started with 500, and then I'm going to multiply it by not the 15% because it loses 15. So that means 85% is still in the bloodstream, and that is to the x. Well, we'll do t, right? Time, the time. So that is my equation. Again, bringing back memories from earlier lessons. Okay, so 10. Here are some points on here. So A, yep, it is a function. B, it looks like a line, so that would be linear. C, if it's linear, it has a constant rate of change. And so then D, we could do, what is it doing each time? Looks like it's going from 7 to 6 to 5 to 4 to 3. We could come up with a recursive, or we could just do an explicit. So I'm going to do f of x equals, well, it starts at 1, 1 plus, and actually I'm subtracting each time, right? Minus, I'm subtracting an x over and over, right? Down 1 over 1, down 1 over 1, down 1 over 1. So that looks like that would be my function in this case, because 1 minus 2, if I put in, 1 minus a negative 1 would be 2. 1 minus a negative 2 would be 3. So yeah, that looks like it works. All right, 11. This one. So here we have two x's in here. We haven't talked about how to multiply that, but since we have two x's as a function, b quadratic, and if it's quadratic, it has a linear rate of change. So D, let's do, again, probably do a graph, but since I don't really have a great way of doing that, let's do a table. So x, and we'll do a y on this one. So if x is 0, we have 3 times negative 6, which is negative 18. We do a 1, 4 plus 3 is 7. 7 times 1 minus 6, that's negative 5. So 7 times negative 5 is negative 35. And we'll do 2. 4 times 2 is 8. So 8 plus 3 is 11. 11 times 2 minus 6, which is a negative 4. That's a negative 44. And then we'll do 3. We're not picking the great numbers to get a repeat, are we? 12 plus 3 is 15. 15 times a negative 3 is a negative 45. Oh, that one's getting close again. They're getting closer together, so we might actually be hitting near a point there. Let's do one more just because I'm curious. Okay, 4. 16 plus 3 is 19. 19 times negative 2 is negative 38, right? 16 plus 3 is 19. 4 minus 6 is negative 2. 19 times negative 2. Oh, It went back down already, so we must have hit a point and are going back down. All right, next, last few. I think we're getting close. Um, Mary Contrary wants to build a rectangular flower garden surrounded by a walkway 4 meters wide. Flower garden will be 6 meters longer than it is wide. So, relationship between the width of the garden and the perimeter of the garden. Well, if I'm thinking about this one, I might actually start with, well, it's a function, right? You know, it's a function, b. Well, what kind of function? Relationship between the width of the garden and the perimeter of garden. I'm actually going to jump to D because I want to do the equation for this to help me visualize what's going on. Let's go again. There we go. All right. So perimeter equals, this is D, perimeter. So a walkway 4 meters wide, I don't know if that makes any difference in here. Flower garden will be 6 meters longer than it is wide. So perimeter is 2 width plus 2 lengths. Well, the length has to be 6 bigger than the width, right? So if I were to multiply all these out, I'd still end up with only 1 W, which means this is actually linear. So it has a constant rate of change. Okay, so here the relationship between the width of the garden and the area of the walkway. Okay, so we know it's a function. We'll do the same thing I did last time and kind of just set this up so I can kind of see what I'm doing here. It doesn't like that. Okay, D. So area is length times width. Well, I'm doing this, I'm going to do a drawing here. So, okay, surrounded by a walkway, 4 meters wide. Relationship between the width of the garden and the area of the walkway. So I'm looking at this is the area I want. So I have to take a length times width minus a length times width, which means I want the area of the walkway, which in this case, if this is my width, it's going to be 4 bigger on this side and 4 bigger on this side, right? Which means it's 8. So my width plus 8 times my width going this way, which is my length, which we already said was 6 plus W, right? W plus 6 plus that 8, because we got the 8 on each side. And then we got to take out the length times width of the inside. W times W plus 6. Wow, that's a lot going on. But the key thing I'm looking at here is a W times a W. We're going to have W's times W's, which makes this a quadratic function. And if it's quadratic, then that means we have a linear rate of change. That was a little trickier. All right, 13. For this one, I have an exponent. And so that means, one, we know this would be a function. Two, B, it is exponential because we have the variable as an exponent. C, that means it has an exponential rate of change. And D, what should we do for D? Should we pick some points in here? This one looks like it might get kind of ugly on there. We do some negatives, it might be a little bit nicer. So let's do X, Y. We'll just do a few numbers since we're kind of running out of space over here. I can scoot this over. All right. So if I put in, let's say 0 minus 2. So 0 minus 2 is -2. So 3 to the second power is 9. 9 plus 4 is 13. If I put in a 1, and I have 1/3 to the negative power, which is 3 to the first plus 1 is 7. And then if I pick 2, anything to the 0 power is 1. 1 plus 4 is 5. So that's how we get to making this not quite so ugly. If I do 3 minus 2 is 1. 1/3 plus 4 is 4 and a third. And then it's just going to start getting a little bit uglier from there. So we are going to stop that one. We got a table. It works. All right. Big finale over here. Let's do this one. A looks like a function to me. E, I see a parabola, so that is quadratic. Quadratic has a linear rate. So happy with the E's there. Linear rate of change. And D, let's do another table because we're getting really good at tables. Change this color so that we're not interfering with the one above. X, Y, looks like an X is -4, Y is 16. So much easier than having to fill it into the equation, right? -3, we're at 9. 2, we're at 1. Whoa, what did I do? 1 and -1. Oh, wait a minute. 4, 3, 2 is at 4. -1 is at 1. And then 0 is at 0. We have a spot at the origin, don't we? All right. And we can keep going if we really want to, but I'm running out of space. So we're going to slow it down right there and just stop there. All right. That is it for this lesson. Thanks for joining us. We'll see you next time.